Okay, good morning, everyone. Hello. Nice to see you. This is our fourth lecture, and today we're going to talk about where all these elements come from. So today's talk will be different from the last talk. Although I'm going to be talking a lot about the nucleus of the atom, and that might be new to everyone. I think the concepts are a little easier this time than they were last time. We're not going to be talking about curved space and infinite universes and all that stuff. And although nuclear physics may be new to many of you, and the word nuclear is kind of scary to people, I still think the concepts are a lot easier. Basically, I'm going to be talking today the whole time about tiny little particles crashing into each other. That's all it is to it. All right, there's three pieces to this lecture, and I think if you keep track of that, it'll be easier to follow. There's hydrogen and helium in the early universe. The second part will be formation of elements up to iron in stars, and formation of elements heavier than iron in stellar explosions. Now that'll make more sense as we go on. Okay, just to review, this is our history of the universe in one big slide. This is a massive slide, and the events of formation of the elements will be, some of it will be very, very early in the universe, before the decoupling of the cosmic microwave background that we've talked about. Some of it we will be talking about the first few minutes of the universe, which may sound crazy, but we're going to be talking about that. And then a lot of what's going to happen with the elements is in stars, and that will happen much later, after the first few 100 million years, and is continuing today. Now, the other thing we talked about, I showed this slide also last time, is the radiation temperature of the universe. As the universe is full of radiation, but as the universe expands, that radiation, like a gas, cools. Expanding gas cools. And so early on, things were really, really hot, like billions, millions, billions of degrees. But they cooled as the universe expanded. And then what we did talk about was that around 380,000 years, the universe was that old, the atoms became neutral, and the universe began to look like what it's looking like now. But before that, it was very different, with the very hot gases. And then 13.8 billion years later, we're at this low 2.725 degrees. And now here is the periodic table. That may be some fond memories from chemistry for a few, or nightmare. But that's basically what we're trying to explain. These are all the elements that we have. Up to something around 94 are elements found in nature. Well, not all of them, and we've also created some artificial elements. So we'll talk about the artificial elements, but we'll try to give an overview of how this came to be. All right, so the elements, first of all, I want to say the elements in the universe are universal. The same elements that are here on the Earth are everywhere else. We see them in the sun, we see them on Earth, of course, and we see them in distant galaxies. And we see them in matter between the galaxies. So the elements are the same everywhere. That's maybe not totally obvious at the start, but that is what we observe. Okay, now to get at this, we have to talk about the structure of an atom. This is a famous picture you've seen millions of times. There are electrons that are floating around in this picture in sort of orbits, clouds. And there's the nucleus, and that's what we're really going to be talking about today, the nucleus of the atom. And the nucleus of the atom consists primarily of protons and neutrons. The protons, that's this here. The protons have a positive charge, and the neutrons have no charge, positive electrical charge. So you might ask right away, that raises a question, well, why doesn't this thing blow apart? Because like charges repel each other. Opposite charges attract, like charges repel. And so what holds the nucleus together? And that is a deep question. And there is another force in the nucleus besides the electrical force. And it's called the nuclear force, or the strong force. And it's a force we don't encounter in our normal life. But it's an extraordinary, it's about, in a nucleus, it's 100 times stronger than the electrical force. So that's what's holding the nucleus together. And the nuclear force acts between protons and between neutrons and between the two together. But the characteristic of that force is that it's extremely strong, but extremely short range. When you get, this is somebody was breathing into the microphone here. Anyway, so it's extremely short range and it's extremely strong. And that strength is what's at the bottom, why nuclear forces are why the nucleus is so energetic. Why when we do nuclear reactors or nuclear bombs, enormous amounts of energy are released. And that force, this is an aside, it's not part of our talk, but you have to remember that force was hiding in the nucleus during all of evolution on the Earth, and we didn't encounter it. And now we've released it. So that's new. And it's a force that we did not evolve with.
Is it radioactive decay, same phenomenon?
Oh, yes. Radioactive decay is part of this phenomenon. And there are two kinds of radioactive decay. One, there's a fourth force called the weak force. And so some of the radioactive decays are there, but we don't need the weak force for this talk. Anyway, this is, by the way, is not to scale. And even though we see this picture all the time, the nucleus is a 10,000th of the size of these orbits. So it's very small. When this all became clear, a physicist talked about it. So it's compared to a fly in a cathedral. Okay, that's the size of the nucleus. But we would never see that. So, but that's how to think of it. Okay, now here's something new. This is the abundance of the elements, the relative abundance of the elements versus how big they are. So along the bottom is the atomic number, which is just the number of protons in the nucleus. And each time you add a proton, you get a new element. That's how elements are defined. So hydrogen has 1 proton, helium has 2 protons, lithium has 3 protons, and then it goes on. Iron has 26 or something. Yes?
Is that abundance in terms of number of atoms or in terms of mass?
You can do either one, abundance in terms of atoms. This is numbers with just saying hydrogen is 1. And hydrogen is the most abundant thing in the universe, and so we'll scale everything to hydrogen. Okay. So for example,
look at the x-axis.
If this is relative abundances, atoms per hydrogen.
Oh, atoms.
Atom. Okay. And so now notice this, and it's not so obvious here, but with hydrogen is 1, then helium is already way down, almost not quite to 100th, but somewhere around 10%. And then the next most abundant element, oxygen, is something like 1,000th. This is 10 to the minus C. These are logarithmics of hydrogen. So hydrogen and helium are the most abundant by far. Hydrogen the most abundant, and then it goes down very rapidly. I mean, things that we're familiar with, like iron, it's something like 10 millionth of hydrogen. All right. Okay, is that kind of clear, how the atomic number is the critical thing? And there's another thing that also comes in, when you add the neutrons to it, that we call that the mass number. And basically that's the number of protons plus neutrons. And that doesn't make a new element, but it makes a new isotope. We'll talk about this. So anyway, if you make a pie chart of the abundance of the elements in the universe, almost all of it's hydrogen, 9% is helium, and everything else is less than a percent. So, and that's of course completely different from what it is on Earth. But the Earth has lost its hydrogen because it doesn't have enough gravity to hold it. And it's lost most of its helium. The helium we see is produced by radioactive decay of things like uranium. But but if you looked at the sun, you would get this kind of a distribution because the sun has held on to its hydrogen. And in many, well, this is, I guess, not relevant, but you can kind of see in when you do cosmological calculations, for some of them at least, and particularly in the early universe, it's a good approximation to say the whole universe is hydrogen, or the whole universe is hydrogen plus helium. It's the first approximation. Okay, now to make the elements, we have to start somewhere. And I think I started the course by saying I don't know how the universe began. Okay, but we have to start somewhere to understand things. And yeah, I didn't make this clear. The thing you can get from this graph is it goes more or less with a lot of bouncing from simple to complex. Okay, there's lots of simple ones, fewer and fewer of the heavy complex ones, big nuclei. And so that's a hint, maybe, that maybe it starts simple and gets more complicated rather than the other way around. And so we're going to start with the universe in this model here that I showed last time. We're going to start when the universe was about a second old. And at that time, we can calculate that the temperature was around 100 million degrees, kind of hot. And and then that is too hot for the atoms to have their electrons. They lose all of those at 3,000 degrees. But it's also too, but at those high temperatures, the nuclei themselves come apart. And so at that time, the universe probably looked like free protons, free electrons, free neutrons, and this radiation, which is just showed as colors in the background. So that's our starting point. And then from this point on, the universe will cool and get to lower and lower temperatures, and then things can happen. So, wait a minute, did I skip something here?
You gotta touch this one.
Okay, so as we go down from 200 million to 10 million degrees, nuclear reactions can start happening. At 10 million degrees, the nucleus is not ripped apart, and we can get nuclear reactions. And that's actually happening in the sun, where the center of the sun is at about 15 million degrees. And nuclear reactions are happening in the sun. So here's the simple reaction. So now imagine this. We started at 1 second, and it's at 100 million degrees, and now it's cooling down to 50 million, and then 20 million, 15 million. And at that point, the protons can combine with the neutrons and stick. And this is very sensitive. Oh, wait a minute, just bear with me. Maybe I'll just use the clicker on the computer. And they stick and they form the isotope of hydrogen called deuterium. See, it's still hydrogen because it has one proton, but it now has a neutron also, and that's deuterium. And that occurs on the Earth. And you've heard of heavy water. Well, that's water made with deuterium instead of hydrogen. Water is H2O, And with D2O, it's still water, and it acts like water, but it's a heavier element. That happens in the early universe. And then, now this gets slightly complicated, but just I'll just go through it, but you just have to remember the result. So we start with protons and neutrons, and we form deuterium. That was the last slide. And then that deuterium can add another neutron and form a still heavier version of hydrogen. And then a proton gets added, and we form helium. So we've created a new element. And that happens in the early universe somewhere around 20 to 50 million degrees.
Can helium form without neutrons? Can you have just two protons and no neutrons?
No.
No.
I don't think that's a known isotope of helium. Helium-3 is known with one neutron. Okay. Okay, well, two things happen here. As the universe cools, it can quickly cool to the point where it's too cold for nuclear reactions to happen anymore. Because once you get below 15 million degrees, maybe it's 10 million degrees, nuclear reactions stop. And the second thing that holds it up is that the neutron, as a free particle, is unstable. It decays into a proton and an electron. So if you had a free neutron in this room, it would decay in 15 minutes. It's a very quick decay. So in the early universe, the nuclear reactions face two problems. The universe is expanding very quickly, and it's cooling faster than these reactions can go very far. And the second thing is it's losing its neutrons, which are necessary to form deuterium. And so the way to remember that in the future, Andy Warhol will be famous. Everybody will be famous for 15 minutes. And that's really true of neutrons, okay? Because they're over with in 15 minutes, okay? So the result is that all of that hydrogen and deuterium and helium form in the first 3 minutes of the universe. And then it's all. Now that's kind of weird to think about. I mean, I think you're probably getting okay to think about the universe as a billion years or millions of years, but 3 minutes is pretty short, but that is what's happening. Yeah.
Is it a halftime of 15 minutes?
Yeah,
or
halftime.
A halftime, okay.
Okay, it's not all gone. Half of it's gone,
Right,
but
okay.
you know, thank you for quibbling there. I'm sorry, Mary. No, that's absolutely true. It's a 15-minute half-life.
What
So-
does the D
so-
represent?
Pardon?
What does the D represent? If the neutron deteriorates, you have a proton, you have an electron, and then on your
A
diagram.
neutrino. That's a neutrino. Okay, a very small particle, and those are formed in. Actually, this is a weak decay because it forms a neutrino. Yeah.
I was just wondering about electron capture. Can happen between, if under the right conditions, electron capture can happen.
Yes,
with
yes.
With a proton
Yes,
and make another neutron with.
that's true, but that happens in neutron star collisions and in supernovae, but it's not happening here. Okay. So when I got out of order here. So what happened? Okay, I got this out of it. So the point is, that's it. The early universe forms mainly helium, small amounts of deuterium. Let's see, the deuterium gets reacted and very tiny amounts of lithium, and some people think beryllium, and nothing else. So there's lots and lots of hydrogen left over. So, and all this happens in the first 3 minutes. Steve Weinberg wrote a really good book, The First 3 Minutes, where he describes all these events in the early universe. And now this is a little complicated. If you don't get it, it's okay. But that's what the cat means. But what I'm doing here is along the horizontal axis is the time And we're starting here from 1/10 of a minute. So 6 seconds, oh, I guess 1 second's about here. And here's 1 minute. And now what you can see is happening here is that starting here. Where's my, okay, starting here, the universe, the helium after in the first few seconds begins to increase, and it increases very rapidly. And by the time that this is 10 minutes here, by the time 3 minutes are over, we've formed all the helium we're going to form. And it's about 9%. And then we also form some deuterium. It's here, and form this helium-3. And there's tiny amounts of lithium. See, this is a 10 billionth of the amount of helium, roughly. So there's tiny amounts there. And that's it in the early universe. That's all we formed. Yeah,
Are you saying that if this all happens the first 3 minutes,
yeah. 3 minutes.
so all the helium that gets made?
So a little bit of helium is made in stars as well, but not as much as was made. Most of the helium in the universe, the big majority of it, is made in the first 3 minutes. 3 minutes is a very long time in terms of nuclear processes, right? These things are moving around speeds of light almost, and so that's a long time. Okay, well, I'm just repeating what I said. It's all over by the time that the universe is 3 or 4 minutes old. It's all the helium. Isn't that neat? I mean, it's... Okay, here's a graph that tries to explain this. This is the history of the universe from the time that this is in seconds down here. So the time it's 1 second old. And so in these first 3 minutes, we form the nucleosynthesis, we form the helium. And then the universe continues to cool. And by the time it's 380,000 years old, we get the recombination and the separation of the cosmic microwave background from matter, which we talked about last time. And that's what we still see. And then when it's 200 million years, we start to form the galaxies. So that's a nice history of the universe. And I actually calculated this, and I used an approximation, but it's very, very accurate. So okay. Believe me on it.
Why does it get dark?
Because it gets dark because the electrons at 3, see, when we're down here at about 3,000 degrees, then the electrons clomb onto the hydrogens, and it forms neutral hydrogen. Before that, it's ionized hydrogen. The free electrons interact a lot with light. Light pushes it around, and that forms this dense plasma. But once the electrons combine, then the photons can go right through. They don't interact with the neutral hydrogen, and the universe becomes transparent and dark. Okay, now here's the deal. We can measure helium abundances in the sun, in globular, in stars, globular clusters, I'll mention those in a minute, galaxies, quasars, and everywhere we look, it's 9% helium. Okay, so it's a tremendous success of the Big Bang. It's a prediction of the Big Bang that is the way we should see helium. So the Big Bang has predicted things that, for example, the steady state couldn't predict, explain very well. I don't know how they dealt with the helium, but anyway. So that's the prediction of the Big Bang.
That last slide, just one minute. Just yeah.
Yeah, you have a question about it? Or?
His observation confirmed that.
Sorry.
That's what I'm meaning. The observations are showing that it's 9%.
So she said oxidation.
No, I said observation, like James Webb.
Yeah, that's what I.
Well, yes, and even before James Webb, we saw this. could see this, you know, you can measure the helium abundance in the sun, for example, with ground-based telescopes and in stars, and quasars. So we've known this for quite a while. So just looking at that again. Okay, now I'm going to mention something off to the side. People have asked me what I did in astronomy a bit. People have been curious about that. I didn't do much cosmology, or hardly any. I was more interested in the interstellar matter, the stuff between stars and in stellar and in planetary atmospheres. But we did do one thing that had at least a brief influence on cosmology. We were trying to understand the atmosphere of Jupiter, what was there. And so we measured methane and then deuterated methane. Well, why did that happen? Look at that. Oh, okay. Ammonia and phosphine. And the deuterated methane is methane with deuterium attached to it. So, and here was the deal. Deuterium is a very weakly bound substance. That's why deuterium is relatively rare. And because unlike helium, when deuterium is, say, found in the sun, it's ripped apart. And so what the deuterium in the sun today is not representative of what happened in the early universe, unlike the helium, which is. And but the idea was that, well, Jupiter is a cold place where the deuterium is not ripped apart, and Jupiter is about 4.5 billion years old. So it gives us a window what the deuterium was 4.5 billion years ago, if we could measure deuterium. And we did. And here's the, you're not going to get all these squiggly lines, but we actually interpreted those. And some of it was deuterated methane, and we were able to measure the abundance. And we found an abundance of deuterium in Jupiter, and for about 1.5 years, that was the best measurement of deuterium in the universe. And somebody else measured it better and stuff. So, so that was the criterion. And here's what it agreed to. The cosmic abundance of deuterium is this over the whole universe. And here it is in Jupiter. And you can see that we wanted to measure it in Jupiter because in the Earth it's been processed and it's different. Okay, and so part of the interest here was, well, let me go to this. This is a current measurement of the deuterium in Jupiter, but when we measured this 40 years ago, we got the red thing, and you see and the line is our uncertainty. And you see that still overlaps with the current value, so our measurement is still okay in that sense, just less precise than what's been able to do before. There is an interesting piece of this. When you look at the deuterium on the Earth, meaning there's oceans, so there's water, then people often wondered where the oceans came from. And the idea was, for many years, that it came from comets, because comets are big ice balls with other stuff in them. And but when finally it became possible to measure deuterium in comets, it was different from the Earth. So that idea that all the oceans came from comets isn't true, and it agrees very closely with meteorites. So a lot of the water in the Earth actually came from asteroids and from meteorites. Some certainly added from comets, but being a unique comet source, that didn't hold up. Okay, so that's kind of an aside. The way we measure it today is deuterium is that we're looking at all these stars and stuff, but the black stuff in between is also full of gas. And when you look at the gas, and the way you do that is, say you have a distant quasar, and the light from that quasar shines through the gas between the galaxies, and it absorbs some of it. And then you look at it. And when you do that, you see deuterium. And the deuterium line, the absorption is very close to the hydrogen line. This is pure hydrogen, but there's so much hydrogen that this is what we call saturated. You can't measure it. It just blacks everything. You don't see anything. This goes down to 0. But you can measure the deuterium, and that's where you get this 2 × 10⁻⁵ density. Yeah.
So the Earth's oceans came from asteroids? Is that?
Yeah, from the solid material that formed the Earth, and that contains water and bound like in clays, and that was released, and that's our best idea now of where the oceans came from.
So, Roger, similar question. So these asteroids were part of when the whole Earth was formed initially, or did you initially you had a dry Earth and then asteroids?
No,
kept
as
hitting?
it formed.
As it formed.
The stuff when the sun formed, not all the material got into the sun. Some of it stayed outside and formed the planets,
Mm-hmm,
and that material condensed to form the planets.
mm-hmm.
And that's where some of the water, and that material contained water, like it contained everything else.
Okay.
Okay, so we now understand where the hydrogen and the helium came from, and a little bit of the lithium. I'll explain the colors later, but well, you can kind of get an idea. So that's all we've explained so far. So we need to think about explaining more. So far we've explained this piece of it up here, but all of this stuff, oxygen, neon, magnesium, and all the other stuff, we haven't explained yet. Notice, by the way, that this curve goes down and then climbs. Iron is very abundant compared to its neighbors, and then it goes down again. And iron, it turns out, is the most strongly bound nucleus of all. That is, it's the tightest bound. Deuterium is not shown here, but so that's the reason for this iron peak, and we'll explain that a little bit more. So that's our next job, is to try to explain that. Where did all these come from? Okay, let's take a break for a few minutes.
Everything all you said.
Yeah, I went too far. This is a comparison of the sun and the earth in size. You can kind of see that the sun is a lot bigger, and a lot of things happen in the sun that aren't going to happen in the earth. I first saw this picture, or a picture like this, when I was in the 5th grade, and it really impressed me a lot. You think of all the great voyages of exploration on Earth in the 17 and 1800s, and it's nothing compared to the sun. So now, if we cut the sun open, this is what we would see. That is, the surface of the sun is near 6,000 degrees. That is the part that you see. It doesn't really have a solid surface, but the part that you see is about 6,000 degrees. And it doesn't matter here whether you talk about centigrades or kelvins or whatever, because at these high temperatures. But the core, the center of the sun, the inner 10%, is about 15 million degrees. And now what happens here is that 15 million degrees, that protons are moving very, very fast. And when 2 protons get together, they both have a positive charge. So they tend to repel each other. So if they're not going very fast, they'll slow down and stop and then go apart. But if they're going really fast, which is high temperature, then they can get close enough to interact, and a strong force can take over. And that's where the 15 million degrees comes from. That's where they can overcome the electrical repulsion, and protons can get together and do a nuclear reaction. And this, just an aside, this is the discovery of fusion, but that discovery kind of explains what happens. You've all seen the famous equation E equals mc squared, which means that the energy is equal to the mass multiplied by the square of the speed of light. And c is always the speed of light in science. Okay, so it's the speed of light. That was an equation that Einstein derived, that energy and mass. Energy is the ability to do work. Mass is what you weigh. Those are equivalent, and that was absolutely new. And Arthur Eddington, an English physicist, derived from this something, had a very great intuition, and and this is from his book, which is not in 1927, long before fusion had been discovered or figured out. But he said, underlined, 4 hydrogen atoms will make a helium atom. See, he didn't know about nobody knew about neutrons at the time, but you know, neutrons have about the same mass as protons, a little bit heavier. And so he said 4 hydrogen atoms will make a helium atom. If the mass of the helium atom were exactly 4, okay, that would show that all the energy of the hydrogen atoms remained in the helium atom. But actually the mass is 3.97. So the energy of mass, 0.03, must have escaped during the formation of helium from hydrogen. That was his insight. That when you form helium, it's less mass than what you started with, and what goes into it. And let me just go on for a minute or so, okay, and finish this thought. So what happens in the sun, and this is oversimplified, but 4 protons, see, there's no neutrons in the sun because they'd be free and they decay in 15 minutes. But 4 protons can then interact and they form a helium. But that helium weighs a little bit less than the 4 protons and it makes energy. And that is where all the energy of the sun comes from. That is how we get the energy. Now, this doesn't happen once in the sun. This happens billions and trillions of times every second. Okay? And it releases, and that energy that's released is part of this, that energy of this originally in the electric and strong force energies of the nucleus. Okay, so you get lots of energy. Now, so this was all worked out in 1938 by Hans Bethe and Charles Critchfield. And they worked out the detailed nuclear reactions which must take place in the sun. There's kind of a legend about this, partly true. Bethe was actually thinking about what has to happen in the sun, and then Teller convinced him to go to this meeting in Washington of the astronomers, and at that time it came out that that the sun was mainly based on hydrogen, and that was new. It had been worked out about 10 years earlier, but by I don't remember her name now, by a famous Cecilia Payne-Gaposchkin. She did that as her PhD thesis, and it was partly ignored, but then it became obvious that it was right, and it was announced at this meeting. And then Bethe went back to Cornell and worked with Critchfield, and in a few weeks, months' time, they worked out how the sun shines. There's a legend that I grew up with that Bethe worked this out on the train back from Washington to Cornell, but Bethe said that's not true. We worked it in the weeks after we got back. Okay, so the amount of energy that you get from this reaction is big. It's enough to build 20 trillion Great Pyramids every second. See, I tried to show the Great Pyramid really is a big thing, and it took a lot of energy to build it. But now, not all of that, that's all the energy that's generated in all directions from the sun. Only a small fraction of that hits the Earth, but still, that's the kind of energies we're talking about.
Roger,
Yeah.
how is that energy anything that we're talking about that is what we use to drive electric cars?
Yes, all the energy on the Earth almost comes from the sun, ultimately. That's what makes us alive. There's a little bit of geothermal energy, heat from the center of the Earth, which is kind of left over from when the Earth formed, but basically most of the energy that we use comes from the sun. Is that your question, Ron? That was Ron Seckel, by the way. Okay, here's the details of that
Yes,
reaction.
yes, it was. Thank you.
Here's the details of that reaction, just for fun. You get two protons just at the top here. You get two protons. Remember, in the early universe, there's a proton, neutron, and the sun adds two protons. They collide, and they give off an electron, a positive electron, and a neutrino, and they form deuterium. And then another proton hits that deuterium, and it forms helium-3. Okay, that's formation of the isotope of helium. Now, exactly the same thing happens somewhere else. This is the same reaction, and you get another helium-3, and then the two helium-3s crash into each other, and they give off a proton, and they form helium-4. That's and energy, and lots of energy. And you see, the net is that you start out with 1, 2, 3, 4, and then add 2 more, that's 6, but then 2 more come off, so the net is 4 protons go into a helium.
What happens to those two protons?
They're ready to react with more stuff in the sun. Yeah, see that center core is full of protons. It's a hugely massive thing. Okay, so but that still doesn't make the elements, but it gives us the energy of the sun. Now, there are very many different stars in the universe. This is, and for size comparisons from stars you may know, here's the sun, here's Sirius, Pollux, Arcturus, but those aren't the biggest stars we know about. This is the biggest star, a type of the biggest star. 5 billion years from now, the sun will use up the hydrogen in its core and make it into mainly helium. When that happens, everything changes, because then different nuclear reactions start taking place. And then the sun will expand, and it'll expand basically about to where we are, almost to where we are. And it'll form what we call a red giant.
How long does something like that will take?
Millions of years, but it's okay. But don't worry about it, because
Once it starts.
yeah, a few million years. But bad things are going to happen to us long before. Don't worry about it. The sun is getting hotter, and a few million years from now, it's going to be tricky. All right. And when this happens, we get a red giant, and you've seen red giants. That the Betelgeuse, that red star in Orion, that's a red giant. And if we cut that apart, then what we see is that the helium, that helium burns in a complicated way. That is, helium reacts now. Whereas before the source of energy was hydrogen, now the hydrogen has been used up, and then helium starts reacting, and at a higher temperature. And then these reactions happen. Two heliums combine, and they form beryllium, but beryllium is a very unstable, weakly bound thing. And a third helium comes in and combines with the beryllium and forms carbon. And that's how we form carbon and oxygen and other things. So it's that helium burning phase of the red giant that forms it.
So the carbon on Earth all comes from some red giant way out there?
Yeah. I'll go into that. Okay, this was all worked out by many people worked on this, but a seminal paper was by Burbage, Fowler, and Hoyle. It's called B squared FH, and this is the only picture I could find of them. It's apparently Fowler's birthday, and they gave him a train. That's why that's there. But Fred Hoyle, you've heard about. He's the one who invented the name Big Bang. He's quite an interesting guy. Margaret Burbidge was an outstanding physicist, astronomer. This is her husband, Jeff. And she did a lot for women in astronomy. When she first got into astronomy, it was still in a pretty primitive state in the early 60s, late 50s. And in fact, she at that time, they did not have women in the 200-inch telescope in Mount Wilson. And so what they did was Jeff, her husband, who was a theorist, he applied for the time to observe. And they gave it to him, and then she did the observing. But everybody knew what was happening. It was just they were trying to get around the rule, and they eventually changed the rules. I don't know what year exactly. They've all passed away now, but so it's quite some time ago, probably in the 70s, I would guess. But I really don't know.
Roger.
Okay, now I just wanted to show an example of the carbon, nitrogen, and oxygen that occur in the universe. Okay, so that's what happens. And the astronomer Harrison said, hydrogen is a colorless, odorless gas, which given enough time turns into people. Yes.
So, I mean, I'm trying to think of the underlying reaction of this atom formation. So when they get hotter and hotter, it allows them to get closer and closer and overcome or be susceptible to this strong force that you talked about at the
Exactly.
beginning?
That's exactly right. Somebody asked that in the intermission too. What happens is that protons are positively charged. Helium, without the electrons, which is ionized, is positively charged. So what the tendency is when two nuclei positive charges come together, they tend to repel each other. So you have to have very high energy. You have to have very great speed in order to get close enough. And that closeness has to be the size of the proton, roughly, for the nuclear reaction, for the nuclear force to take place, which is attractive. And so therefore, you need high temperatures in order for nuclear reactions to take place.
Yeah.
Okay.
Because you'd think they blow each other up, but it's just the opposite.
Right, because it's when they get close enough together, it's an attractive force. Holds it together.
This picture.
And this is why it's so hard to build fusion reactors. We've now built them and they work, but we're not yet at the point where they actually generate commercial electricity. But the nuclear reactions that take place in a fusion reactor, like the one in France, which was just in the news, the temperatures are higher than in the sun. The temperatures have to be over 150 million degrees in that reactor. And that's very difficult to do.
Roger, go back to that.
Okay, yeah.
Go back to that picture, the one that's this.
Oh, this picture, yeah.
This picture was taken on a trip where we stopped at a rest area in order to see the eclipse of the sun.
Oh, cool, okay.
That's why everybody has those funny sunglasses.
Yeah,
Right, and I took the
Okay.
picture.
oh, yeah. Congratulations. And that's Mark in the back, right? And then Lois and Helen and, or, yeah. Lots of people, okay, so that's fine.
So Roger,
New Yorker or any place else for permission.
Okay. Yeah, I didn't ask your permission, but.
Roger,
Yeah,
is it difficult to have a fusion with those high temperatures? Because there's no container that you can put it inside of that will hold it?
that's right. At 150 million degrees, everything melts. But what does hold it is the charged particles are susceptible to the magnetic force. And what you do is you build a magnetic field which can contain this hot gas. And that's the very difficult thing to do because the magnetic fields tend to fall apart and so on. But the French recently got, if I remember right, they recently got a reaction at that temperature to go for 20 seconds or something, which is a huge step ahead. And I just want to mention something about the cosmology. If you look at 13.1 billion years ago, a Webb spectrum, you notice that we already have oxygen and there's hydrogen, and we also have neon. So even at this very early time, these reactions have already taken place in stars. And that has been something of a surprise to us. The Webb is pushing this way back. Okay, so we made the stars, made all these elements up to iron. But the problem with iron is it's the most tightly bound nucleus that there is. And anything beyond that doesn't generate energy. You have to add energy to make it happen. So the reactions don't go beyond iron in stars because you'd have to feed in energy to make it happen. So how do we make the things that are beyond iron? Like uranium and stuff like that. By the way, this I thought was kind of interesting. This was found in Tutankhamun's tomb, and it's an iron dagger, but this was before what we call the Iron Age. So about, what was that, about 1450? And what they did was they found meteoritic iron. Some iron meteorites fall, and they found those, and they used that iron to make. So it was the only iron object found in his tomb. It must have been much more valuable than gold, for example, because they didn't know how to smelt iron at that time. So now now to respond to a question, the red giant isn't the end point of stellar evolution. Once the red giants get going and have been working for a while, they become very unstable. And you get minor explosions or big explosions, and the material explodes. This is the Ring Nebula in Orion, and this star in the center has exploded and cast off a lot of its envelope. And so that is how materials like carbon get back into the interstellar medium and are available to form new stars and planets. And that's how your carbon came from. It formed in early stars long, long ago, which went through their stellar evolution cycle and put this material back into the interstellar medium, where it was now available to form a new star, which was the sun 4.5 billion years ago. Here's some more planetary nebulae, kind of very photogenic things, and you can see there's more than one explosion that happened. These red giants are very unstable things. We had to do an observation that involved red giants, and I learned to my sorrow that there's no two of these red giants that are the same. It seemed like we couldn't fathom very easily. That's an aside. Okay, now let me go beyond iron, because I'm racing here, so I'll take some questions in a few minutes, okay? But how do you get beyond iron? And I think here's a hint. If you look at oxygen, it has 8 protons and 8 neutrons. Then you get to something heavier like iron, it has 26 protons and 30 neutrons. Now there's other isotopes, but that's the abundant one. But then gold has 79 protons and many more neutrons, 118 neutrons. And you go to uranium, it has 92 protons and 148 neutrons. So see, there are a lot of neutrons coming in, and that's kind of a hint. We got to look at the neutrons to make these heavy elements. I'm not sure how, it's kind of just a hint, a sense, maybe. And what happens here is that this is an example of something that happened in 1987. You may remember it. There was this star, has the arrow pointed to it, and it blew up and became this star for a few weeks. And then it went down again. And this is called a supernova. Stars, certain kinds of stars, not all stars, but massive stars can explode in their later life. Rather than the sort of quiescent small explosions that we saw in the planetary nebula, there can be colossal explosions. Here's one from a distant galaxy. This is M82. Here it is before, and then suddenly this appeared for a couple of weeks. And it's kind of hard to, but when you look at this carefully, M82 is a big galaxy. It has 200 billion or more stars in it. And this one star is outshining everything else, including all the others. So this is a gigantic explosion when a supernova goes off. It's an unfathomable. And roughly, to give you an idea, in a nuclear weapon, a few grams of material are converted from mass to energy. right? Hydrogen bomb is big energy. So it's a few grams there. But in a supernova, a third of the mass of a star is converted.
You said it only lasts a few weeks?
Yes,
And then what happens?
it fades down and, okay. And here's an example. This is the Crab Nebula. I showed a picture, a JWST picture last time. This is a Hubble spacecraft picture. And this is the star that was recorded by the Chinese astronomers in 1054. And it was bright enough to see in the day for a couple of weeks. And it faded. And then when we look where the Chinese showed it, we see this today. And it's very clear that this is right, because when you measure the speed of these gases here and assume that the speed hasn't changed much, it took about 1,000 years to get from the center out to here. It's 1,000 years ago. And then when you look in the center, there is a remnant called a neutron star, which is the pulsar. You've heard of pulsars. And what the remnant is after one of these explosions is a star made entirely of neutrons. And the star is only the size of about something about 10 to 15 kilometers in diameter. So it's about as big as Santa Cruz, but it has a solar mass of stuff. Wow.
Why are they
So,
not-
and there's neutrons. Sorry?
What's it made of?
Neutrons.
Yeah.
Neutrons. What happens is that that center of a massive red giant, that center eventually even consumes the helium. And then there's no hot stuff energy to hold it up. And then gravity causes it to collapse. And it collapses enormously into a very small object. And if you're up to something like, I think the limit is something like 3, it's not known exactly, but it's something like 3 to 4 times the mass of the sun, it'll form a neutron star. If it gets more massive than that, it can't even stop at a neutron star and forms a black hole. That's a different topic. Anyway, now we have a neutron star and we have lots of neutrons. That's just what we needed. And so here's a typical example. Bunch of neutrons get together, they form this big thing. And typically it's unstable. And so some of the neutrons turn into protons and we get a new element. And that's how we can form those heavy elements in supernova explosions.
How does the neutron become a photon? What happens to the neutron that
It decays.
acquire a positive charge?
Missed an electron
No, it emits an electron, yeah, and a neutrino.
and gamma ray.
And now, so another thing can happen. Let me play this. I got ahead of myself. Okay, that's an artist's conception. The neutrons make a good, play good music too. So I got a little ahead of myself. So an explosion, supernovas can make these heavy elements, but there's another way. More than half of our stars are binary stars, 2 of them. So it can happen that both of the stars turn into neutron stars. So I have 2 neutron stars, and then they can collide. So it's a rare event, but it happens. And we detected that by when that explosion happens that you saw in the animation, it's an enormously energetic event, and it's so energetic, it jiggles the space around it. And it causes what we call gravitational waves. The space itself begins to send out waves of gravity. And that they're very weak, not many, but we can do that now. This is the one of the 2 laser interferometer gravitational wave observatories. Gravitational waves were first predicted by Einstein, who said we'd never detect them, but he was wrong about that. And the way to detect them is that you have this thing with two arms, and you send light across the arms back and forth, this arm back and forth. And so you measure the distance from the center to the end very, very precisely. And when a gravitational wave comes by and starts bending space back and forth, the wave, say it comes this way, will cause the deflection to be different in this arm than in this arm. And and that gives you a gravitational wave. And you remember in the news that was first possible in 2015. This worked. And we have two of these detectors because it was all new, and we figured in order to make it believable, it had to be detected by two detectors. So one is in Louisiana and one is in Washington. There's also one in Italy and another one in Japan. This one was built a little bit later than the others, and one in Germany, although that was just used for development, including development of this device, but it's not big enough to actually do an astronomical work, but it's very important for development. So this is what's going on. Here's the LIGO, and it detected black holes all the time, but in 2017, it detected something different. And what we have here is the amount of stretch of those arms, the difference in stretch of those arms versus time, plotted here. So the time is in seconds. So the merger of two neutron stars, its last moments were kind of like in real time in that animation. Oops, let me go back. And here is they've made the signal into sound, and you can see, and that was the collision. And then the bell is a different detector, namely gamma rays. And that was highly energetic photons. And that's one reason we knew that it wasn't a black hole, because black holes don't give off light, but this was seeing a lot of gamma rays. And so let me play that again. And you'll see that the gamma rays came in a couple of seconds after the gravitational wave signal. There. And here, and this event was also detected by ground-based telescopes. And here's the before picture, and then that neutron star collision caused this light. And that's 120 million light years away. And again, because a black hole wouldn't give off any light, we knew this was something else. It was the collision of two neutron stars. And when two neutron stars collide, you have a lot of neutrons. So you can make a lot of stuff in that event. By the way, the Einstein prediction was that the gravitational waves and light waves would move at the same speed of light. And the fact that it is 2 seconds difference, and 2 seconds is 2 seconds, but we believe that that's just because when the neutron stars collided, there was very, very dense gas in that explosion, and it took the light, bounced around in that gas, and it took it 2 seconds to get out. But even if you take the 2 seconds, the speed of light of the gravitational waves and the photons is within 2 seconds in 120 million years. So that's a part of 10 to the 15. I don't think we know anything to that precision. So that's what happens. So lots of neutrons when those two collide, and we find that can form gold and silver, mercury. So that's where your gold came from. And so that now explains that down here, this is supernovae and neutron stars. So now this is that periodic table again, and now the colors are to indicate. You can see that. Can you read that all right? Yeah. where the stuff came from. And so the Big Bang fusion is hydrogen and helium. And then, for example, carbon comes in dying massive stars, nitrogen. And so in, like red giant stars. And then the explosion of the massive stars can also form elements. And then where are we here? So a lot of these were formed that way, but merging neutron stars, for example, here's gold, primarily comes from merging neutron stars, so does silver. These two. Mercury comes equally. So it's complicated, right? I promised you it wouldn't be totally simple, right? I'm trying to simplify it. So lots of things happen, and these nuclear reactions are just like a chemical reaction, right? I mean, when you eat something, there's all kinds of chemical reactions going on in your gut and stuff. So it's not totally simple, but trying to get an overview of it. That's
So on the Earth, Roger, when there is a spot like the mother lode, all this gold is concentrated in one area. What does that mean? I mean, did that have?
We have to ask a geologist that. That's how stuff was moved around as mountains formed and stuff.
It's a good thing that these things are really far away from us, right?
Yeah, it is good, actually. If the sun will not supernova. It's not mass enough to do that. But if it did, it would sterilize the Earth completely. I mean, there'd be nothing left. Yeah. So there's a big picture here now that kind of you have interstellar nebulae, clouds, and pieces of the clouds condense and form a protostar, which is a forming star with some material left around it, which makes the Earth and planets. And then it converts into a sun-like star, makes energy and helium. That eventually, in billions of years, turns into a red giant. Red giant continues to evolve, forms a planetary nebula, and gives off some of the elements that have been formed. And that's available to make new stars. So there's a real cycle in the universe. And of course, and it's a little more complicated than that, because more massive red giants can explode and form neutron stars and form supernovae and make neutron stars. And that makes some of the heavier elements. And then colliding neutron stars also make heavy elements. So a lot going on. But basically in the universe is building up its retinue of heavy elements. That's the evolution that we have going. Well, I just thought I'm gonna end in a few minutes. Excuse me, losing my voice. I showed you the LIGO thing to do gravitational waves. There's a new experiment being built called LISA, the Laser Interferometer Space Antenna. It's built by the European Space Agency, although United States has participation in it. And instead of 4-kilometer long arms, it'll be in space with 3 traveling detectors, and which are separated by 2.5 million kilometers. And that will, and roughly the size of those arms is the wavelength of the gravitational wave that you can detect. So the current ones we have detect waves on the order of kilometers or so. This will be much longer wavelengths, which means lower frequencies. And this would be able to detect something we haven't seen at all before. But what LIGO is detecting is black holes which have masses on the order of 10, 20, 30 times the mass of the sun. But this thing would be able to detect galactic mass black holes, the black holes which are on the size of millions of solar masses. And we haven't seen a collision like that. But LIGO, if that happens in the universe, LIGO will be able to detect it. So, and this project has been approved. They in fact did a test launch of a smaller version and it worked perfectly. And so they went ahead with the project and it should be launched in 2035. So that will really tell us a lot. It will also, in addition to detecting giant black holes, there's something I haven't talked about at all, but I'll just mention it. There's, during the time of inflation, which we talked about last time, it's thought that that's a pretty wobbly process and there might be gravitational waves generated then. And those faint gravitational waves from the, now not second of the universe, but 10 to the minus 35 seconds, one with 35 zeros over it, might be able to detect those. I'm losing my voice, so so you better read this. Okay. Yeah.
How often are these collisions happening, these explosions happening? You say, you know, we had that one from 2015, but
Yeah.
are these happening frequently all over the universe and we just don't detect them?
Not very frequently. First of all, supernovae are very well known. Roughly in a galaxy like ours, 200 billion stars, there's a supernova once every 30 years. We don't see the ones in our galaxy that well, but we see them in other galaxies, which are a clearer view. And that's roughly the time that's come out. Once every 30 years, you get a big supernova. The neutron stars, that I don't think that's as well known. And we've found the one in 2017 and one other possible, but they're still working on that in the last 10 years.
It would seem though that with, as you described, how many billions of galaxies there are, that this thing must be happening more frequently somewhere in the universe, you know? Don't you think?
More frequently than what?
Than what we've seen.
Oh, yeah, we're not seeing all of them. We have a range that this can see, but the gravitational wave thing goes pretty far, you know, hundreds of millions of light years, billion light years. So it's seeing a lot of the universe. So they're not particularly common events, but they happen. I wish I had a better answer for you. If I don't know if anybody has estimated, maybe they have, of how many neutron stars collisions do you get in a typical galaxy? And I don't know that number. I don't know if anybody's published, try to figure that out.
I mean, it could be fast, right? I mean, really, if you think about all the different galaxies.
Oh yeah, then there's a lot. I mean, there's 1 trillion galaxies in the known universe. So that's, and the universe may be infinite. And infinite's always impressive. I mean, you know, an infinite universe is mind-boggling, right? Because if it's infinite, everything could repeat, right? Infinite, okay, we could have exactly the same as what we are because there's always more. Yeah, okay, well, I'm going to end with a poem. Thou canst not stir a flower without troubling of a star, which a poet in the 19th century wrote. He sensed, I think he kind of sensed this connection, even though at that time it wasn't known. Okay, and the next time we're going to talk about dark matter and dark energy. That's it for today.
So where do neutrinos fit? Neutrinos.
Well, they're